Okay, we shall go now to the example. It is already in Gretl. So file is named CS School. And now we will make the model for the regression of student-teacher ratio or class size on a test score. First, we will do the scatter diagram. So I marked two variables and then choosing XY scatter plot. Software is asking me which variable should be on the x-axis. On the x-axis is always independent variable. In our case, student-teacher ratio. Okay, and here is the diagram. You can see original data, student-teacher ratio on horizontal axis, test score on vertical axis, and you see already the line of the model. Here is the equation, but we will do the entire model after this. So we will choose model, ordinary least squares. In the space for dependent variable, we will put test scores. We can set it as a default so that we don't have to always transfer data here. In this window, we already have the constant. It will be our beta 0. But for beta 1, we need student-teacher ratio. Okay, move it here. Then we will click OK. And here is our model. So this is beta 0. This is beta 1. These are the standard errors of our coefficients. This is the sign of their statistical significance. Both our coefficients are statistically significant, but about this we will talk a little bit later on. Also, we have here r squared at the moment, 0.05. We have adjusted r squared. We will also this explain later. And we have here standard deviation and standard error of regression. In a file section, you remember that we can save it as an icon or we can see it as equation if we click here. So in the shape of the equation, we have our coefficients. Okay, so this is how you do it in the Gretl software. Let's go back to presentation. Again, this is general model, and then we have with exact coefficients. So what these coefficients mean? When it comes to beta 0, it shows theoretical value of dependent variable y, test scores, with independent variable x, student-teacher ratio equals 0. Of course, it is only theoretical value because it is impossible to have any scores if you don't have students. But from the mathematical point of view, we need to have this coefficient or this intercept. When it comes to beta 1, it shows the average change in dependent variable y when independent variable x is increasing for 1 unit. So in this case, please notify that this is negative. So when student-teacher ratio goes up, test scores goes down. In this case, unit change in student-teacher ratio will cause decrease in test score on 2.28 points on average. Very important that you always need to underline that this is on average. So it won't happen for every district in California, but on average for 420 districts. You see again our graph. You see the regression line. And it is calculated on the basis of our true values of x. When we put them in this equation, we will get y hat. So we will get theoretical values, and they will be all on this line. You can connect them with one straight line. So since our x-axis starts with 14, this is the smallest size of the class, you don't see the point where is beta 0. We need to move this vertical line to the left where x is 0, and then you can see where this blue line crosses the vertical line. This is the point where our beta 0 is. Where is our intercept? This is why it's called intercept, because it's intercepting the y-axis where x is 0. Now we can start asking questions when we have our model. For example, what if we hire teachers so that class size is 20? What is the predicted score? So instead of x, we will put 20, and then we can calculate that we can expect the test score for the class size of 20 students per teacher is 653.3. What if size is reduced by 2? It means actually that our beta 1 coefficient, it is, as you can see, this. When we change the student-teacher ratio by 2, what will be the change of test scores on average? So in this case, on average, we can expect that increase of test scores, because we are reducing the class size, the increase of test scores will be 4.56. The question is, what we can expect if the size of the class is only 5 student-teacher ratio? Well, it is outside of our data range, because as you already know, the size of the class, minimum size of the class is 14, so we don't have data for these small values of class size. So we can calculate it, but it is not reliable because we don't have data, we don't know what is happening outside our data range. So we can only make forecasts for this interval here, from 14 to, let's say, 25 or 26 class size, because here we have data, we know what kind of variation we have. The next title is measures of fitness. So it shows us how to measure ability of estimated model to explain the data. How good is our model? We have actually two ways. One is R-square, so-called coefficient of determination, and it is explained as fraction of the variation in y explained by variation in x. So how much of the variation of y is explained by x? The second measure is standard error of regression. It shows how far our original data y on average from the estimated line. So on our picture, it says how much on average our red crosses are far from the line, from the blue line that we have. R squared, it is very famous, very simple to implement and to comment, but it is not always reliable. But anyway, this is the fraction of the sample variance of y explained or predicted by x. We can do prediction like this. So on the basis of the average value of y, we can say what will be the y in the future, but this is not really reliable. We can do it also like this, by developing by implementing the ordinary least square method and then developing the equation. So what you think, what is more precise? Of course, the second one is much more precise because it much better follows the variations of your data. You can see that on the picture also. So we have our original data, these dots, this is average value. And forecast for that will be only, again, the average value of y. But in the case of regression line, we can much better predict, so we can better illustrate and catch the variation of our original data. So you can expect the coefficient of determination R squared is much higher for this regression line in comparison with the line of the average. So R squared is the ratio of the sample variance of y hat to sample variance of y. So it is the ratio of variation of your theoretical data in comparison with original data. It is ratio of explained sum of squares to total sum of squares. So all variation we can define in the following way. So we have total sum of squares. These are the difference of our original data and the average value. So this is total variation. Squares so that all can be positive. On the other side, out of this, the explained sum of square are the difference of theoretical data from the average data. if we compare these two values, we can get R squared. So we are comparing what is explained in comparison with the total variation of our data. R squared always is in the interval from 0 to 1, or from 0% to 100%. So we can really easy can comment on this and say, for example, if this is R squared is 90%, that we have explained 90% of the variations of our dependent variable y. So let's talk more about sum of squares. We have also one other variation. It is sum of square of residuals. This is the difference between original data and theoretical data. These are actually our residuals. So we can actually say the total sum of square, total variation, consists of explained variation and unexplained variations. So explained sum of square and sum of square of residuals. If we divide explained sum of square with total sum of square, we get R squared. But also we can get it on the other way if we just say 1 minus sum of square divided by total sum of square. Also we can do it like this, so we can calculate the correlation between dependent and independent variable and square it. So where are these variations if we look at our data? So remember, I will show it on this part here, on this dot here. So total sum of square are the difference between original data and the average data. So this is original data, this is average data. So entire line, green and red, are actually total variation. So when it comes to explained variation, this is the difference between theoretical data and the average data. These are our theoretical data, our regression line. So the green line is actually explained part of our data, difference between theoretical data and the average data. Sum of square of residuals is part that is unexplained. So as you already know, it is from our data to the theoretical data. So this is the best way for you to see which part is what. So total variation, explained variation, and unexplained variation are residual. The second measure of it is standard error of regression. This is the estimate of standard deviation of regression error UI. So as we already know, these are our residuals, and we are seeing on average how far they are from our theoretical value. The higher the value of standard error of regression, our model is weaker. So this is how we are calculating it. Just sum of squares of our residuals and then divided by the number of units minus 2. Why 2? Because we have two coefficients. This is our number of degrees of freedom. We have beta 0 and beta 1, so 2 coefficients. And this is how we get our variance. And out of this, sum of standard error of regression is square root out of the variance. It is always expressed in the units of measure of dependent variable y. So in our case, with our class size, it is always expressed in test points that we have. So on average, we can say how far are our original data from our theoretical value. For example, you already know, you already saw the results. This is the copy from the equation U from our model. R squared is 0.05, so it is really small. Only 5% of variation of test scores is explained by class size. Only 5%. These standard errors are standard errors of our coefficients. Standard error of residuals is not here. I will show it to you after this. So we are going to our model. Standard error of regression is here. So I already commented on R squared. It is here. Standard error of regression is here. So it is 18.5, which means that on average, original data of test scores are far from theoretical data by 18.15 58 test points. So this is the comment for standard error, and this is the end of this example.